Unit for satellite access. So what we are going to say in this unit is that this unit is divided into three parts. One deals with the modulation and multiplexing techniques. Second one deals with the FDMA, TDMA, and the CDMA techniques. And the third one deals with the split spectrum techniques being used for satellite access. So in this session, we'll be seeing the first part of your unit for satellite access. So the first topic in that is your modulation. Okay. So I think most of you all are familiar with the term called modulation. Modulation is termed as transmitting our message signals or information signals over a carrier signals for better transmission and efficient communication. The characteristics of either amplitude, frequency, or phase will be varied in accordance with the characteristics of the carrier signal, and then it would be transmitted to a longer places. And in addition to the modulation, we'll be seeing the multiplexing technique, where the multiplexer means that we are having a 2 power n inputs and a single output. Depending upon the selection lines, the data will be multiplexed at the transmitter side, and at receiver side it will be demultiplexed. So the modulation and multiplexing techniques jointly together are being used at appropriate places depending upon the requirements. So let us see what are the terminologies that we need to see in the modulation and multiplexing. Is that a two value and a multi-value encoding technique, baud rate and bit rate. So all these three terminologies you all are very much familiar than me. So which is given by the Nyquist theorem, which relates speed and bandwidth, then the Shannon theorem, which relates speed and noise. So we'll be using our digital encoding. Encoder or decoder will be used appropriately. We'll be seeing a carrier, modulate, satellite access are your frequency shift keying, amplitude shift keying, phase shift keying, and the quadrature amplitude modulation. So any of this can be used depending upon the requirement. And in multiplexing and demultiplexing, we might be using frequency division, time division, wave division, or code division. Anything might be used in multiplexing, demultiplexing systems, depending upon the requirements. So this is an simple example of your digital signal transmission, how your signals are being increased. You can see that at the top we have a sequence of binary digits 010010. You can see here. This is being transmitted to an encoder. So that will be sent in this format after the encoding part. Okay. So this has two values, 0 and 1 at an interval t, 1t, we call it as 1t. So for 1t, 0 will go, for another t, 1 will go, for another t, 0 or 1. So for every time period, there will be only one symbol being transmitted. So this is an example of that. Then bitrate will be 1 per every time. Okay. 1 bit will be sent for every second or every cycle. So 1 bits per second. So baud rate, it will be m is equal to 2. So baud rate pulses per second, number of pulses per second, how much it is? 2 here. So you get m is equal to 2. So in the same, if you use in half a cycle, you can see the second diagram. Second pulse value same 2. Okay, 0 1, 0 1 is being sent. M is equal to 2. Half of the cycle is sent. So half of the cycle is sent means for every 1t cycle there will be two sequences, 0 1 in the first case, second case 0 0, third case 1 0. So the time period is reduced. So this increases the bit rate by reducing t. Okay, so there should be always two stage, three stage, and fourth stage, right? And within time interval t. Okay, 1 0 0 1 0 1 1 0. So this is your steps. So increasing bitrate by increasing m corresponds to your baud rate. So this was given by Harry Nyquist, who was born in Sweden. In the year February 7, 1889 was his DOB. April 4, 1976 DOD. He was at Bell Laboratories, Texas, USA, and he was also in association with the ANT, AT&T. This Harry Nyquist is well familiar for the Nyquist rate, Nyquist criterion, Nyquist stability, Nyquist filter, and Nyquist sampling theorem. So this sampling theorem is what we are going to concentrate on in communication. And you all probably would have studied all those 6 inventions by or 6 postulates by Harry Nyquist. So the basic question is how many pulses could be transmitted per second and recovered through a channel or a system of band limit is addressed, or he addressed this question appropriately. So which was published in Telegram Transmission Theory Transactions AIEE Volume 27 during the year April 1928. Nyquist paper. So this is what your Nyquist theorem relationship between transmission speed and the system bandwidth. So we have an encoder, we have a transmission system or a channel bandwidth, we have a decoder receiver. So I send a signal 010010. Okay. So how to interpret with Nyquist theorem is that given a system or channel bandwidth of B, the minimum T will be 1 by 2B, the maximum signal rate D will be 2B pulses per second, which is equal to 2B log to the base 2 m bits per second. So to transmit data in bitrate, the minimum bandwidth of a system or channel must be bandwidth greater than or equal to D by 2 log to the base 2 m hertz. Next comes the Shannon's theorem. So Claude Shannon, who also worked at the Bell Laboratories, was born on April 30, 1916. His DOD is on February 24, 2001. He is a mathematician and electronic engineer at Bell Laboratories. He has invented a Shannon theorem, which is information theory. Then he had, along with Fano, he had discovered the Shannon-Fano coding. He has given postulates on channel coding theorem, the chess which is played on computers, and he is a master in cryptography. Okay, So the basic question is that how do bandwidth and noise affect the transmission rate at which information rate can be transmitted over a channel? This was his addression. He had addressed this question's answer appropriately. So communication in the presence of noise is the journal Proceedings Institute of RE, volume 37, 1949. Claude Shannon. So then is the Shannon's theorem, which is more concentrated on the channel bandwidth. So the relationship between the transmission speed and noise, we have encoder sender, we have transmission system. So the maximum signal rate or maximum data speed or channel capacity can be obtained by the 10 log S by N signal to noise ratio measured in decibels. Width would be 1 plus S bar N when the baud rate equals B and its channel capacity is C is equal to B log to the base to 1 plus S bar N signal to noise ratio, which is totally measured in bits per second or bit rate. So the channel capacity is what your Nyquist-Shannon's theorem shows that the maximum rate or channel capacity of a system or channel depends on bandwidth, signal energy, and the noise intensity. So thus, to increase the capacity, three possible ways are there. One is the increased bandwidth, raise signal energy, reduce noise. If B is fixed, the bandwidth is fixed, we have to increase signal to noise ratio for increasing transmission rate. So Shannon theorem will let us know that how we cannot send data faster than the channel capacity, but we can send data through a channel at a rate near to its capacity. We cannot overflow the data, but within the prescribed channel data or the channel bandwidth, we can send our data. So that was his ambition, and he has achieved it. Next is the digital encoding. So you all are familiar with the Manchester. The return to zero, non-return to zero, non-return to zero inversion, non-return to zero, which are used in RS-232 and RS-422. Then the AMI used in ISDA. Biphase Manchester is used in LAN HTTP3 systems. Next is the RS-232 cables configuration, which is taken as an example in the case of carrier and modulation. So the important facts is that the RS-232 cable connects two devices in a shorter distance, the range of less than 15 meters. It cannot be propagated far because its signal energy rapidly becomes weak with the increase of transmission distance. A sine wave will propagate farther. The sine wave is analogic signal. A signal can be carried by the sine wave called carrier for longer distance. So if you choose a modulation scheme of AM, we modify the amplitude. If you choose FM, we modify the frequency. If you choose PM, we modify the phase, which we call as phase modulation. Amplitude modulation, frequency modulation, and phase modulation. So these are some of the examples. We have a signal. We have the AM, amplitude modulated. You see, we have the frequency modulated. here I distinguish the carrier and the signal, and we have the phase modulator. Next is next topic is your digital modulation schemes, where the input of the signal is a digital signal and the output is a analog. So there are three different digital modulation techniques, starting with the frequency shift keying, FSK, amplitude shift keying, ASK, and the phase shift keying, PSK. So most of you all are familiar with this shift keying techniques, which you are studied in your digital communication. So the extension of this PSK gave us an enormous channel bandwidth utilization, which led to the evaluation of QAM. It is a combination of the modulation of amplitude and phase both together. So there are different types of QAMs being used depending upon requirements. 4-bit QAM, 8-bit QAM, 16-bit, 32-bit, 64, 128, 256, 512. So if you see an 3 cross baud rate, we'll be using an 8 QAM. So 2 power 3 is equal to 8. So we get 8 points. You can see on the axis, we get 8-bit representations. You can see 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. Then this 4 zeros till 4 ones. So this is an example of your 16-bit QAM transmitters section with its signal constellation. We have a signal, then it is being split up into two, which is given to impulse generators, HDFF, the filter, then it is being modulated. So if you have any queries till this, you can type in chat box. After 5 minutes, we'll proceed for the next topic. Since there are no queries in the chat box, I further move on to the next topic. Voice, data, and video. The modulation and multiplexing techniques that were used in the initial stages were analogic in nature, which are adapted from the technology developed for. Then there was a change over to the digital voice signals, which made the long distance traveling of the signals much easier. So the communication carriers to mix digital data on telephone, fiber optic cable transmission standard systems were being introduced with megabits per seconds, and the kilobits per seconds voice channel capacity had stuffing bits, and words were added to the satellite data then streamed as required into the space. So primarily for video, the satellite access provided carrier to noise, but in older receiving equipments, at system and satellite specification, KU band satellite parameters were being deployed. So for voice, data, and video. So this is an block diagram of voice, data, multiplexing, and demultiplexing circuit, which was used in a satellite link. Okay, you can see that a voice with the help of coder and decoder, which we called as codec, was transmitted with 62.5 kilobits per second. A 8-bit synchronous generator, which was operated at 15.625 kilobits per second. We had a telephonic interface, which we used either dial type or hook status type. Okay, touchpad type or dial type. We had two selection lines, A1 and A2. Then depending upon the requirement, if you select A1, voice would go. If you select this, the telephone interface will go. So that was being synchronized by the clock operating at 250 kilohertz. Then it was given to a frequency shift keying modulation. Then from there, it was transmitted using optical cables to the receiver. The left hand side is completely your transmitter section with the data from your communication control. So which was transmitted at data rate of 250 kilobits per second. Then at receiver, we have an optical receiver which receives that and demodulates them by using the FSK modem. Then a clock receiver, DPLL. This clock loop was being used, operating with a 250 kilohertz of frequency, which was as in your transmitter. Then demultiplexer, the codec, then an 8-bit synchronous detector, which is an inverse of the 8-bit synchronous generator your transmitter. Then we had your telephone interface with the same selection lines. And coming back to the modulator and demodulator, this is some of the examples. A modulator will accept bit sequence and a modulator carrier. Demodulator will accept a modulated signal and recreate the bit sequences. So a single modem, a device modem will do both modulation and demodulation. Just modulator plus demodulator, we take those terms, MO from modulator and DEM from demodulator, which we call as modem. Let's see an example of modem here. Computer site 1, we have a modem. M represents for modulation, D represents for demodulation. Then we have the long distance wires, the connecting parts, connecting connections, connecting segments. Then at modem at your receiver, at computer site 2, we have a cable as used in transmitter. So this is an internal structure of your hardware components of a modem, how it looks. This is the outer box, how a modem looks. The computer at site S1, Modem 1 RS-232 cable can be used over a voice telephone system. Modem, then we have a computer right side too. So how does the data are being sent efficiently? You can see computer A, computer B, computer C are being operating on three lines which are good from site 1 to site 2 with the data rates DA, DB, DC. So this is how you can see a multiplexer, demultiplexer from all the PCs or systems they are connected. Then they are being traversed in a fast line or single line. At receiver, same multiplex, demultiplexer. Then at site 2, same. So this is how this is being done. Multiplexing is a set of techniques that will allow simultaneous transmissions of multiple signals across a single data link. What is used inside a MUX and a DMUX is this. Okay, we'll be using FDM, TDM or CDM. Any queries? Any queries you can type in chat box. Next topic is analog digital transmission system. Data would be always continuous in analogic, whereas it is discrete in digital. So we need to know about the signaling, which is continuously varying electromagnetic wave with respect to the sequence of voltage pulses. So in transmission, we need to see the difference in how the attenuation is handled rather than the shifting towards digital transmission despite larger analogic base. So the shift from analog to digital transmission system is meant for improving digital technology, data integrity. Repeaters take out the cumulative problems that occurs in transmission. Thus, the transmission of signals will move further with the same available bandwidth over a longer distances. So it would be easier to multiplex large channel capacities with the digital. So it would be easier to apply encryption to digital data rather than to analog data. There will be better integration if all the signals are in a single form. Therefore, they can integrate voice, video, and digital data. So, what is the digital data analog signal is given in this slide. All the signals must be converted digitally data to an analogic signal. So, such a device or in such a place a modem would be best used between a serial and a modulated carrier signals. So to send digital data using analog technology, the sender generates a carrier signal at a source tone in the frequency of 1 to 2 kilohertz that will look like a sine wave. So for this, the following techniques might be used to encode the digital data into analogic signals. So the resulting bandwidth is centered at the carrier frequency. So amplitude shift modulation or keying will be used for varying the amplitude of a signal. It is used to transmit digital data over an optical fiber. Frequency shift modulation is preferred where we use two or more tones which are near the carrier frequency, which is used in full duplex modem signals. So full duplex is your signals in both the directions. In phase shift modulation systematically shifts the carrier wave at uniformly spaced intervals. They are used in satellite accessing. So the first type of multiplexing is your frequency division multiplexing. A set of signals are put in different frequency positions of a link or a medium, where each of the bandwidth of the link would be larger than some of the signal bandwidths. And in each signal is modulated with its own carrier frequency. So examples are radio, television, telephone backbone, satellite. All uses frequency division multiplexing technique. A1, B1, C1 operating at different frequencies are modulated on a single carrier. You can see example. Then at receiver it is being demodulated as 1, 2, 3. Next is time division. So multiple data streams are sent in different time in a single data link or medium. And the data rate of the link would be much larger than the sum of the multiple streams. The data streams take turn to transmit in a shorter interval, which are widely used in digital communication networks, TDM. So computer A, computer B, computer C have been transmitting some animations. So first A1 is sent, B1, C1, then A1, B1, C1. And computer 2 it is being received by computer A2, B2, C2, which is sent from A1, B1, C1. Examples of FDM and TDM you can see. Since you all are familiar with the multiplexing schemes techniques, this diagram will give you a more illustration of what an FDM and TDMA is. You can see the top is your FDM, bottom is your TDM. You can see in the example of FDM, we have signal 1 in red color, signal 2 in green color, signal 3 in blue color. So at different frequencies in the range of 10 to 20 kilohertz, these are being transmitted. You can see the source band are being present in between each and every signal 1 red, signal 2 green, and signal 3 blue. Frequency division multiplexing. Whereas in TDM, if you have, for example, 5 conversations, so any one will be selected at a particular time. So for example, if conversation A is going on, so A will be connected to A. B is going on, B will be connected to B, depending upon the time. So this is TDM example. Next is an important topic, wavelength division multiplexing. So this wavelength division multiplexing would have used in your, would have studied in your optical communication, where unit number 5 dealt with the WDM concept, how it is being done, which uses the concept of FDM, frequency division multiplexing, sending multiple light waves across a single optical fiber. So, followed by the WDM, we have the split spectrum. Split spectrum modulation is used as a system that is used to combat jamming and eliminate errors and to give a secure communication. So the spreading the signal over a wider bandwidth for reliability and security is done in the spread spectrum modulation scheme. So its carrier frequency is not fixed and it dynamically changes. So such changes are controlled by the pseudo-random sequences, which we call as PN sequences. Then the signal is represented in code domain. As we use nowadays, OTPs, one-time transfers, one-time password for transferring of any information into our mails or OTPs through banks, through others, wherever we do. So those uses this spread spectrum modulation scheme, where pseudo-random sequences are being generated and sent to the appropriate user. So that user has to authenticate or verify the security. Pseudo-random codes or sequences. So in code division multiple access, different codes are assigned for different signals. This is an example of your wideband CDMA, which was implemented by the 3GGPK. Third project, third group project partnership by entity. So the WCDMA or wideband CDMA concept is that It uses 4.096 chips per second, having a direct sequence CDMA spreading with variable multi-code operation. Both in uplink and downlink will be using the same. So the codes with different spreading gives around 8.5 kilobits per second. You can see the structure of the wideband CDMA's frequency versus time, how it is being utilized. So any queries till this? Any queries till this? Because next we are moving on to the multiple access scheme, which are the basics for your satellite accession. Any queries, type in chat box. 5 minutes time is given, then I'll go for the next topic. Since there are no queries, I move on to the next topic. Need of multiple access. Satellites are built and deployed for the common good of one or more regions. So this means a lot of people will need to send and receive data through the satellite without major mishaps. So for this purpose, one may use several multiple access techniques. So out of them are FDMA, TDMA, CDMA, and DAMA. So the satellite access techniques are being classified as such: pre-assigned, demand assigned. So in pre-assigned we have the FDMA, TDMA, CDMA, where FDMA is further classified into fixed, single carrier channel, single channel per carrier, and multiple channel per carrier. For every carrier, we'll be having a single channel as SCPC, and for single same carrier, we'll have multiple channels, which comes under FDMA. Then we have the TDMA, then we have the CDMA. So in CDMA is divided into frequency hopping and spread spectrum system of direct sequence. So this all comes under pre-assigned control multiple access techniques for satellite accession. Whereas in the demand assigned control, we have the single carrier, sorry, single channel per carrier, demand assigned multiple access scheme, then demand assigned time division multiple accessing, then we have frequency and time division multiple accessing, demand assigned multiple access scheme. So these are the classification of satellite access techniques that is being used. So as the name suggests, operates by dividing the available bandwidth between users on the basis of frequency. A group of users may be allotted a range of frequencies, and each individual user can use a limited frequency shifted channels within that range. So the earlier FDMA used FM waves, which were very much easier to utilize. So this is a FDMA structure: time versus power. Frequency is divided. User 1 is given one frequency, user 2 is given another frequency, user 3 is given another frequency. So this is an example. So frequency versus time. We have 1, 2, 3, 4, 5, 6 different images separated on 6 different frequencies. How it works? The frequency division multiplexing with the FM is transmitted to satellite from earth stations. They are received by the common transponder. So then the microwave filters are used in the earth stations to separate signals within the transponder. Then the corresponding earth stations will receive data back from the transponder and the data get demultiplexed. If the frequency assigned has to be changed, all the earth stations filter must be retuned. This will cause an long idle times also. So this is how frequency is shared in FDMA. Let's see, we have channel bandwidth assigned for every frequency, which is pre-assigned. Frequency is shared in FDMA. Signal 1, 2, 3, 4, 5, 6 divided into different frequency bands. So a single channel per carrier, this SCPC technique, will have a number of small mobile earth stations that can transmit and receive data over a single transponder, so which will enable satellite telephony. So this can also help utilize the whole wide bandwidth of the transponders efficiency. So this is your transponder 1, transponder 2, where the carrier frequency is divided in megahertz. where the frequency of transponder 1 for 10 USA, 10 USA and 10 for Chile. 3714 megahertz carrier frequency was being used. In transponder 2, same transponder bandwidth 36 megahertz, 20 carrier frequency was used for the USA and Chile 3771, 20 10 megahertz. So the transponder bandwidth of 56 megahertz is divided into 10 as such 1, 2, 3, 4, 5, 6 with 10 kilohertz guard bands. So the advantages of the FDMA is that if the channel is not in use, it will become ideal. Efficiency when the number of stations is small is higher. There is uniformity in traffic. No need to go for network timing. No restriction regarding the type of baseband or type of modulation being used. Anything we can use it. The disadvantage is that the presence of guard bands uses more bandwidth. So this also requires RF filtering to minimize the adjacent channel interference. ISI or the channel interference is more in FDMA. Next comes the TDMA. Time division multiple access. The time division multiple access which is shortly called as TDMA is being spread over the spectrum. The whole bandwidth is used by a user for a fixed amount of time. So one user will use one fixed amount of time, another user next, then next, then next, and it goes on. Depending upon the number of users, the time is being allotted. So all the practical TDMA signals are digital, and hence their advantages over the traditional FDMA systems. The problems of non-linearity are not present here because the whole bandwidth of the transporter is used only by a single signal. However, the need for the higher bit rates, the presence of ISI can be a big problem. In TDMA, a number of earth stations take turns transmitting bursts of radio frequency signals through a transponder. All the practical TDMA systems are digital. The TDMA is an RF multiple access technique that allows a single transponder to share the information in time between the RF carriers from different earth stations. The RF carrier from each earth station shares a transponder that is sent as a burst at a specific time. So at satellites, bursts from different earth stations arrive sequentially. The transponder carries a near continuous signal. This is the structure of TDMA, time versus frequency versus power. You can see for every time, same frequency is used for user 1, user 2, user 3 until user n. So the total time division is divided by for every users. Number of users decides that. You can see green is one frequency, gray is one frequency, light green is another frequency, blue is another frequency, dark green is another frequency, violet is another frequency. So depending upon the time, depending upon the frame or slot, every user is being given a chance to transmit their information. How this TDMA works? The multiple earth stations transmits data in shorter bursts such that they reach the transponder in a sequence. This transponder simply outputs all the incoming data into a continuous stream of serial data with short guard times, where all the earth stations must be synchronized for the signals to arrive within the positions allotted to them in a frame. So the received serial data can be recovered using the synchronous attained between the transmit. Bits and pieces is out of our scope. Advantages of this TDMA is that it is a flexible bit rate, no frequency guard band is required. We need not go for precise narrowband filters. Extended battery life is being available. This is the most cost-effective technology for upgrading a current analog system to a digital. There are some disadvantages also, which is that it requires time synchronization, which is lacking. The demand high peak power on uplink is being a major issue in TDMA. So any queries in FDMA and TDMA, you can type in chat box, such that after that I'll proceed for the CDMA. Since there are no queries, I move on to the next topic called CDMA, Code Division Multiple Access, where all the users can use the whole bandwidth all the time. Okay, so the data need not be synchronized or to be filtered. It can allow users it can allow users with more needs utilize the bandwidth more while considering it when it is ideal. So the transmission times or frequencies are irrelevant here, and there is hardly any spectrum allocation. So currently used method is your DSSS, it is direct sequence spread spectrum modulation. So this is what for every user, for every time, every frequency, there is a specific code being assigned for user 1, user 2, user 3 till user n. So at 1 by T chips for every chipping rate. So this is an example. So frequency is separate, time is separate, different time slots at different frequencies. Any of your signals can be transmitted. You can see from this diagram you can easily understand how a code division multiple access works. So how this works is that the earth station can code the data based on a CDMA code, obeying a set of rules defined by the organization. So this code can be 16 bits to several thousand bits long. Since multiple stations can saturate the bandwidth without much effort, this system is highly efficient. So the receiver needs the same code used by the transmitter. So this is the structure of CDMA. The input data stream RB bits per second is being transmitted as A. The pseudo random noise bit sequences at a chipping rate are be given to your mixer. Then at C we get the signal, CDMA signal, so which is being transmitted to the modulator. Then this is being given to D. Then a thermal noise effects are added, noises are added at point E, and interference of signal is being obtained at your receiver and other CDMA signals. So this is at F. Then a demodulator, an appropriate frequency oscillator is being used as a local oscillator to demodulate the signals. Then at G, then at H, by using your identical pseudo random noise sequences which was used at transmitter is the same used here to decode the original sequence. So the bit timing and deduction takes place here, where we get the original data output stream as similar to the input at transmitter. This is how code assignment occurs in CDMA. Next is the comparison of the frequency division multiple access, time division multiple access, and CDMA. All the three in a single. So from the diagram itself, you can see time versus frequency for a single period of time. Different users are allotted different frequencies. And in TDMA, for a single frequency at different time slots, the users are being allotted. Whereas in CDMA, with the different frequencies at different times or at the same time, all the users can be accommodated. Comparison of FDMA, TDMA, CDMA. So any queries till this, you can type it chat box. So with this, complete today's session. In the next class, we'll see DADM DAMA, demand access, how it works, where it is used, how it is used in satellite, how it is the structure is,